substances, and very often the starting point to getting to those substances is an alcohol. Okay, so these reactions that are real important for us in terms of creating other substances that we'll study later on this semester. Okay, we alluded to this reaction a moment ago. If I have an alcohol and I protonate it with an acid, I get this protonated form that's a good leaving group. And then by nucleophilic attack on this carbon here, I can create the substituted form. This will be particularly good for HBr, somewhat good for HCl, and somewhat good for HI. In other words, if I want a bromide, chloride, or iodide from an alcohol, one way to do it is just simply put that alcohol and dissolve it with HBr, HI, or HCl. HBr is particularly good here.
It's particularly good because it's selective? Or why?
It's more, the bromide is a better nucleophile than the chloride. The chloride tends to give us lower yields. And the iodide is such a good nucleophile, we have some other side reactions that take place. So we get really good yields with bromide, acceptable yields for the other two. Now, in this reaction, the alcohol is protonated and becomes a good leaving group. Third degree and or tertiary and secondary alcohols react with bromide by an SN1. What am I saying there? What does an SN1 involve?
Could have a carbocation.
Carbocation. So we need to recognize that there may be some rearrangements involved here. Primary alcohols react via SN2, which means we don't have to worry about rearrangements, but we have to worry about stereochemical inversion. So if we're dealing with a carbon that's chiral, okay, the chirality will be reversed. Do you remember when you knew all this stuff?
Yeah, it's like the umbrella when it pops out.
Okay. So there are downsides to each of these possibilities, but provided that they're not an issue, okay, then we don't have to worry about them. And this is a good way to get a substitution with, say, bromide. Reaction with HCl. Chloride is a weaker nucleophile than bromide, and so one thing we do is we put the chloride in the form of zinc chloride. So this is similar, but zinc is a transition metal. You can find that on the periodic table if you don't trust me. And transition metals form complexes, and so what happens is I put zinc chloride in solution and I get a solution of chloride as the zinc chloride dissolves, but the zinc complexes with the alcohol. And that's just like protonating the alcohol. That complex OH group is a good leaving group when it's got the zinc texture. So the zinc chloride, by complexing with the alcohol, makes the alcohol a good leaving group. So we're not protonating here, but we are complexing the alcohol. Do you understand, remember what complexes are?
Like it's forming something more intricate, like a...
Yeah, we see it in biology. For example, I take an iron 2 or iron 3, and the heme nitrogens around the iron complex with it. And those nitrogens hold the iron in the middle of the hemoglobin molecule. Okay, that's the same kind of chemistry. We're talking about complex formation for metals that we find in the transition part of the periodic table, the transition metals. And zinc is one of those. It's not as good at complexing as iron or as manganese and some of the others, but it's still pretty good. And that's what's going on here. Now, once this happens and chloride replaces the alcohol, then I get a compound, I get an alkyl halide, chlorohalide. And the chlorohalide solubility characteristics are different from the alcohol. This is actually used as an identification test. You will see this later on, trust me, in the laboratory. Later on in the laboratory, you're going to be doing an experiment where you're trying to identify an unknown liquid and an unknown solid. And one test for the alcohol is the Lucas test. Okay, and it only works for smaller alcohols that are pretty water soluble. Okay, and so that means liquids that are usually about 6 or 7 carbons and less. All right? They dissolve in aqueous solutions that contain the zinc chloride. This is done, by the way, in concentrated HCl to help the process along. If the reaction takes place, a water-soluble alcohol is turned into a water-insoluble chloroalkane. And so you can tell when the reaction takes place because a clear solution becomes cloudy. The cloudiness is the formation of this halogenated form of the hydrocarbon, and it starts to, it scatters light because it's not dissolved anymore. Does that make sense? So what you do is you take an alcohol, a suspected alcohol, treat it with acidic zinc chloride, and if the solution turns cloudy, that says you've got an alcohol. More important than that, how fast it turns cloudy tells you what kind of an alcohol. Primary alcohols react extremely slowly, probably not in the time frame of the test. Tertiary alcohols should react almost instantaneously. Secondary alcohols should take a few minutes. And you can read the instructions in your lab manual. And you can then say, all right, I'm pretty sure I've got an alcohol as one of my unknowns. You try it, you do this Lucas test, which is what we're talking about here. And if you get an instantaneous fogginess in the test tube, what does that say?
Tertiary.
Tertiary alcohol. Okay, so this reaction not only is useful for producing the chloroalkane from the alcohol, but it's useful for diagnostic identification purposes. All right? Now, here's the mechanism we're talking about. Here's the complex. Here's the zinc. It takes a pair, I don't want to get too off track, but how do complexes work?
That formal chart, or its ability to have, isn't like if it's a 2+ or 1+ or whatever?
You have, the transition metals have empty orbitals, most of them, d orbitals. And then there's a place for them to put electrons.
Oh, okay.
Yeah, and in fact, they act as Lewis acids. What are Lewis acids?
Lewis acids comes from
Electron pair acceptors. Lewis bases are electron pair donors. And so my alcohol acts as a Lewis base, donates one of its non-bonding pairs of electrons to zinc, which has got some d orbitals it's not using, or some orbitals it's not using, and that pair of electrons forms a covalent oxygen-zinc bond. That's how complexes work. Unfortunately, in general chemistry 2, there should be a chapter in your, I'm not encouraging you to go back to your general chemistry 2 textbook, but there's going to be a chapter in there on complexes. And because of the topics that are normally covered, we usually don't get to that in general chemistry 2. But it's important in biological reactions like hemoglobin. What other metals are useful in biological systems? Magnesium.
Yeah.
And it does exactly the same thing in chlorophyll. Okay, you've got a magnesium, excuse me, complexed into a heme-type structure in chlorophyll. That holds the magnesium in place, and the magnesium is crucial for the chlorophyll to do its job. And again, it's a complex. And so this is just a non-living application of the same kind of bond formation. All right, we're using zinc rather than some of the other metals that are commonly observed forming complexes. Okay, so in this particular case, once the complex is formed, this guy is a good leaving group because as this bond breaks, as my nucleophile attacks, I've got this guy, which is kind of just an inorganic salt that's not acidic or basic at all. It's just a nice, neutral, fairly stable substance, good leaving group. And the chlorine has attacked here, and now, what once was perhaps a nice water-soluble 1-butanol, it looks like, is now 1-chlorobutane, which is not water-soluble. That's what the solution turns cloudy. Problem is that you're looking at it right now and you're sort of seeing how this works. By the time you actually try and do the Lucas test, you're not going to remember the chemistry. You're just going to follow the instructions and look for cloudiness and just look for the symptoms and the signs. This is the chemistry that's being described there. If we do this as an SN1 reagent, or reaction, again, we complex the alcohol, and because this is such a good leaving group, it leaves the carbocation behind. Then the chloride comes in and completes the reaction in the final step. In terms of testing purposes, if you look at this reagent, it doesn't really matter whether we're talking about SN1 or SN2. The results are the same. A clear solution becomes a cloudy solution if the reaction occurs. And the reaction will occur if we've got tertiary or secondary alcohols, and the time it takes is symptomatic or indicative of the kind of alcohol you've got. Now, problems using simple HX, where HX is HCl, HBr, HI, poor yields of alkyl chlorides, particularly. Elimination competes with substitution. What are we saying there?
Pulls off the other H, forms a double bond.
Yeah, because chloride is somewhat more basic than bromide, we protonate the alcohol takes off, and I've got a carbocation, or this can be an E2 as well, and the chloride acts as the base to remove the other hydrogen, and I get an alkene rather than a substituted product. Okay, and we clear back when we talked about substitution elimination, this was discussed. Carbocation, if it forms, is prone to rearrangement. And as a consequence, we have some fairly limited usefulness for this because of these considerations. But never fear, we have other ways to do this that we've yet to discuss. Here's an example with bromo substitution. We take our alcohol, 3-methyl-2-butanol, and this illustrates one of the problems. And remember, HBr is pretty good at this. So HBr protonates the alcohol, bromide replaces it, and look at the product we get. What's up with that?
Rearranged.
Rearrangement. Notice that the alcohol is a nice secondary alcohol. I protonated. Secondary alcohols are prone to do the substitution through an SN1 mechanism. The water comes off, leaving a carbocation. Well, it's going here. We protonate the alcohol, great leaving group, and I've got a secondary carbocation here. And in the next step, that secondary carbocation enjoys a hydride shift to create a tertiary carbocation, to which the bromide is then attracted and added. And so we get a rearranged product, rather than what we might have been intending to do in the beginning. How are you doing? So, what we do, an alternative is to use the phosphorus halides as an alternative. Good yields with primary and secondary alcohols, good yields with PCl3, PBr3. For iodine, we can't use PI3. What we do is we put elemental phosphorus, this is called red phosphorus, and elemental iodine together in the reaction mixture, and they form PI3 in situ, and then the reaction occurs. And we might have made mention of this.
Isn't that something about?
Yes. This is used in the in illegal methamphetamine manufacture. In that reaction, pseudoephedrine and ephedrine have an alcohol that needs to be replaced as part of the reaction. And so as part of that reaction, this PE or PI2 combination is used to get rid of the alcohol. In that particular case, the alcohol is replaced by